Today we learn about Lempel bridge, run length encoding and bit plane encoding. Besides that, image compression standards and image fidelity. LZW compression. LZW is a dictionary-based algorithm. Unlike other algorithms that need to send the dictionary along with the decoder unit, this algorithm doesn't need to send it, which means the dictionary is created at the decoder side to form the data itself. How does it happen? What it does, it has a pre-built dictionary from 0 to 255, which means for the dictionary entry from 0 to 255, it has corresponding values 0 to 255. So to encode consider this is the string that has to be encoded. So the first value 10 is taken and checked in the dictionary. 10 has a dictionary entry in the value 10 is found in the dictionary entry position 10. So the next value is added along with 10, which means 10 and 15 is together checked now. But 1015 is not in the dictionary, so that is added to the dictionary at the position 256. Since the value of 10 was found at an entry 10, it is the encoded data would be 10 for that position. Now 15 is again checked. The value 15 enters at the entry level 15. So the next value along with 15 is checked here. Since 1520 is not available in the dictionary, an entry is created in the dictionary at the next position available. And again, the value of 15 was found in the 15th position. So 15 is again given here. The next position is 20. 20 is again found in the 20th position. Similarly, it happens. So the next position along with 2089 is matched. Since 2089 is not found about here till here, 2089 is added in the 258th position. Similarly, this happens until all the strings are added. But once we come here, 1520 is already found in this position. So what happens is 257 is added at that position, and the next string along with 152010 is added to 260th position. So this continues, and the encoded data would end up looking like this. So this is LZW. The next one is run length encoding. Run length encoding is a lossless method that works best on continuous gray levels. Consider, for example, 55555, the RLE encoded as 57, which means the gray level 5 is repeated 7 times. Consider a stretch of gray levels in an image as 555555555 or so and so. As this is a string, this would be encoded as 5925463918, which means the gray level 5 is present 9 times, the gray level 2 is present 5 times, the gray level 4 is present 6 times, the gray level 3 is again present 9 times, and the gray level 1 is present 8 times. Run length encoding works best on continuous gray level and can be combined with many other compression methods. The next compression model we are learning is bit plane encoding. What happens here is the gray levels of the images are converted into their binary equivalent. The planes are created on the binary bits, but we can come to conclusion that for the bit 128 and 127, the representation would be extremely different, which means instead of compression, you end up having a file larger than the actual one. So, but how is this used for compression? A little modification here, and this would be perfectly fine. For example, since we are considering bit 127 and 128, first what we do is, rather than finding the binary level, we find the gray level. How is gray level found? Gray level is found using this formula. G of m is equals to A of m into, which means XOR A of m plus 1, which means G of 0 would be A of 0 XOR A of 0 plus 1. That means A of 1, which means 1 XOR 1 would be 0. Similarly, all the gray levels of G0 to G7 for 127 is found. Similarly, gray level for 128 is found. Now you can see that from the gray level, it does not differ much. So using this modification, we can construct bit planes on them, and these gray codes can be now encoded using RLE and thus compressed. After so many less compression, we come to a point of lossy image compression. This is irreversible completely, which means once the image is compressed using a lossy compressor, it cannot be completely decompressed back. Which means the data that is lost forever. But if the data is lost so much, why is this used? This is used because of the high compression rate that is provided. Some of the features of lossy image compression is that it is easy to implement. There are multiple standards available worldwide. The most commonly this is the most commonly used. For example, the JPEG image compression standard. Some of the standards for bi-level images, which means the one we take in a Xerox, that is or black and white, where rather than different colors, the gray level is considered. Some standards for them are JBI G1 and JBI G2. And some standards for continuous still image, which means the colored images or photographs, are JPEG. Image fidelity. Image fidelity can be defined as the closeness of an image to an original source and an ideal source, which means rather than defining on the quality of an image, that how good the image looks when modified, we define a term in fidelity, which means how less is it transformed. So there are two ways to find out. First is the subjective fidelity criteria, and second is the objective fidelity criteria. In subjective fidelity criteria, what happens is the fidelity criteria is checked as per the human eye, which means I would give what you would do to check the fidelity criteria of two photographs is you give the photographs to a set of people and take their opinion, and where they would rate it on a scale from 0 to 5, whether it is good or not nice, or whether the images are completely different or etc. The next one is objective fidelity criteria. Objective fidelity criteria uses equations to measure the error in the reconstructed file. Some of the measures of error are mean square error, which is calculated using this formula, and peak signal to noise ratio, which is calculated using this formula. So that's all for today. Chapter 7, module 7 is completed, and thank you for learning with Junk Mice.